Hello everyone. So today we are going to start chapter 8. So chapter 8 is the first chapter where we're going to start using the Riemann integral and the ability to integrate multivariable functions and try to now use the concept of integral to deal with different things. So first what we're going to learn is in chapter 8 is something called line integral. So let's show you what that is. So let's recall that a function, let's say f, actually I'm going to use a capital vector f, that map from Rn to Rn can be represented as a vector field. Now notice that when we have a function that maps from Rn to Rn, there are definitely many different ways to interpret it. One way that we use to interpret a function that maps from Rn to Rn is a coordinate transformations, provided that this function is one-to-one, has an inverse. However, there are definitely different ways to interpret it, and another way to interpret a function mapped from Rn to Rn is to interpret as a transformation that transforms something in the domain to something in the range and form a new image. Here we are not interpret as a transformation, but instead we interpret that this function forms some kind of vector field. So how does that work? Well, this is how it works. We'll take a function vector f, which have an input in Rn and map into Rn. We'll define the input to be position vectors in Rn. So therefore, it represents a position in space. And actually, I don't need to specify in Rn because we already know. And graphically, we'll represent them using dots. And then the output of the function, we will define them as direction vectors. And they will represent using arrows. So a very simple example to illustrate this process is to give a very simple example of a vector field. So here's my x, here's my y, and let's say we are identifying the following dots to be my input. And of course, technically speaking, we have like infinite number of dots on the xy plane. But let's just say we're looking for just nice and simple points that have integers coordinates. So let's say I have these 25 points. So these are my input, which in this case in R2. And then I can now try to define the output, but the output not as a separate position, because if I do, I will need to graph this picture in R4. We don't know how to do that. Or we separate this into two separate R2 picture, where one is for the domain and one is for the range, which also contain the image inside. But no, we're not. We are containing everything within one R2 graph, where we just use two different ways to represent the input and output. So the input would be this blue dot, and let's say the output would be vectors that go like this. And that's just and someone might remember seeing this picture. Where everything just get pushed outward. Like explosion, everything pushed outward from the origin. Okay, so in this case, this would give us an example of a vector field. In this case, our function f mapped from R2 to R2. All right. Now that's not new to you because you have seen this back in chapter 5. It's one of the things first thing I taught you in chapter 5. We talk about gradient field, where I show you that gradient is technically is the function map from Rn to Rn, and therefore in order to graphically represent this the gradient, we have to draw it as a vector field where you separate the domain and the range as two separate geometrical objects. That way you can show the correspondence between them without increasing the dimension that you have to draw your graph. So what we talk about right now? Well, imagine the following. Let's say let g of t, or let's say let g be a curve that went from R to Rn. Let g be a curve in Rn. And actually, I'm going to go and give this curve a name. I'm going to call this curve alpha. So let g of t, maybe I'll write that, so that way we can define the domain, the independent variable. So let g of t be a function map from R to Rn. Let it be the curve alpha in Rn for, let's say, from A to B. Then what happens is, if I were to draw this curve could start at some points, and then it would just go through this space, and it might end at some other points. There you go. So here's my curve alpha. Now, notice the following. Here's the important part. When this curve goes through the same R2 where capital F is, every single point on this curve would have some kind of vector pointing out of it based on vector F, capital F. What we're going to try to find out is the following. Is what if we can add all these vectors together? What would that add up to? That's what we're trying to figure out. So important to note is the following. Note, as this curve travels through vector F, every single point on curve alpha will have a vector given by F. And what we try to figure out is if there is some way to add them all up. So in this case, I'm going to go and loosely use the word sum. The sum of all these vectors from the curve alpha is given by what we call a line integral of alpha over the function vector F. Oh, actually, you know what? Maybe I probably write it this way is better. The line integral of, because you're actually integrating F. So a line integral of cap vector F along the curve alpha. So that probably a better way to write it, because you are actually doing a line integral of capital vector F. I'm going to go and define to you what this line integral is, and right now you have no idea what this line integral actually calculate. It will calculate some numbers, okay, but you have no idea what this number is yet, okay, but we will talk about what it is, don't worry, okay, but let's get through the idea of what is a line integral first. So let's say, here's my definition. Let's go define what is a line integral. Let's say we're given a function vector cap F that map from Rn to Rn. So therefore we can say that F is a vector field in Rn. So important to understand is that we are technically speaking integrating a vector field along a curve. That's basically what we're doing. We're going to let g of t be the parameterization of a curve alpha in Rn over, let's say, the domain t go from A to B. Then we can now define the line integral. Then the line integral, so this is what I want to define, the line integral of vector f along the curve g of t is basically given by this formula. And right now you have no idea how this formula come about, but I will show you where this formula come to once we learn how to use it and be able to evaluate with it. All right, so here's what the line integral formula is integral from A to B vector f of g of t. So that give us like all those vectors that travel along G by using a composition. And it makes sense because when you use a composition, we restrict the domain of vector cap f to just the curve G of t, or the curve alpha. And dot product G prime of t dt. Now that part you probably don't understand why that is, but as I say, once we understand what this line to actually evaluate, at least like the basic concept of it or where it come about, then you'll understand a little bit better. And of course, a line integral can be used to calculate a lot of different things, but we're just going to talk about like the most basic interpretation. Kind of like when you see a regular integral from BC calculus, what can it represent? Well, we can always try to interpret it as the area under the curve, but it can also represent a lot of different things. Just like Riemann integral can be represented as volume under a surface, but it can also be used to calculate a lot of different things, depending on how you interpret the function and how to use the integral. So we're going to talk about the most basic interpretation of a line integral in a little bit, but just want to give you a definition and learn and want you to know how to use the formula first. So some of the things I do want you to pay attention to is the following. Number one, this is a single integral. So meaning that this is actually an integral that you learn how to do back in BC calculus with independent variable t. Okay. 2, this is a definite integral. How do I know it's a definite integral? Because they have limits. It is a definite integral. So therefore, the result is a numerical value. It's a number. What does that number represent? We have no idea as of now. Okay, but once again, we will talk about it, so we'll get to it. So what I want to do next is to show you some example on how to use this formula so that you can know how to calculate the line integral. And once you can do that, then we can try to understand what does this number that we figured out means. So here's our first example on evaluating line integral. Let's say given vector cap f of x, y, z is equal to x squared, y squared, z squared. So here, this is basically our vector field. And let's say we're given g of t equal to t squared t to the third. From, let's say t go from 0 to 1. So here is our curve. Okay. How to identify vector field? Not because it's just simply because it's called capital F, vector F. It's because in this case, this function capital vector F is a function map from R3 to R3, which satisfies what a vector field would look like. And why is g of t equal to t squared t to the third a curve? Not because it's named g, but rather because the function map from R1 to R3, which fit the definition of what a curve would look like. Okay, so keep that in mind. This is how you identify what function it is, not by the letter that they're being used. Because remember what I keep telling you guys is that there are way too many things that we mathematicians want to use to represent with letters. So therefore, a lot of these letters are going to get reused. So if you get too tied down on using the letter to identify what you have, you find out that you get yourself all confused when maybe a problem uses the same kind of vector or same kind of letters for different things. So let's see. So how about let's just find the line integral. So let's say we're just going to find the line integral of vector f along the curve g of t. There you go. So how do you find this line integral? Well, just use the formula. The formula is this: integral from a to b vector f of g of t dot product g prime of t dt. So it's just a matter of trying to find everything we need to plug into this formula so that we can evaluate. So I like to do things, little by little. So first thing I notice is that I know a is 0, b is 1. That's from the inequality. Next thing I'm going to do is, since g of t is t squared t to the third, then that implies that g prime of t must be 1 to t3 t squared. So that take care of that. And next, I do need to find vector f of g of t. So that just means vector f of t squared t to the third. And so that's my x, which is t. Y is t squared. And z is t to the third. So therefore, I'm going to now plug into f, and therefore I will have t squared t to the fourth and t to the sixth. So now I have everything I need. Now I'm going to write out my integral. So my integral goes from 0 to 1, t squared t to the fourth t to the sixth. That's f of g of t. Dot product g prime, which is 1 to t 3t squared dt. So that seems pretty straightforward. Now I'm just going to carry on my dot product. So 0 to 1, it will be t squared plus 2t to the fifth plus 3t to the eighth dt. So that's a pretty simple integration. So we're going to integrate this. So it becomes 1/3 t to the third plus 2 over 6 t to the sixth plus 3 over 9 t to the ninth. Evaluate from 0 to 1. And notice when I plug in 0, this whole thing goes to 0. When I plug in 1, it's basically 1/3 plus 2 6 plus 3 9, which they are all technically 1/3. So 1/3 plus 1/3 plus 1/3 give you 1. So this line will come out to be a value of 1. Now, what does this number 1 actually represent? Well, that's what we're going to try to explain to you later on. For now, just be able to find this number. So that way you'll be able to do the problem. All right, let's give a second example to try out. Okay, so here we go. So kind of same thing. Let's vector f of xy equal to xy, and let g of t equal to cosine t sine t for t between 0 and 2 pi. So that's one way to write that is t such that, which is kind of like this little e, 0 to 2 pi. And I'm just going to go ahead and ask you to find the line integral. Find the line integral of f along g of t. Okay, so I strongly recommend that you take a minute to just pause the video and go and try to do that on your own. And then once you're done, you can check and see if you did it right. And of course, I'm just going to go and keep doing. So if you want to go and try first before you watch how I do it, go and pause the video, okay? So I'm going to go ahead. So therefore, we'll be integral from a to b, vector f of g of t dot product g prime of t dt. So let's find this. So a is 0, b is 2 pi. G of t is cosine t sine t. So therefore G prime of t would come out to be negative sine t cosine t. And vector f of x of g of t would equal to vector f of cosine t sine t. And since the function f actually just keep everything the same, so that just turned into cosine t sine t. So now I have everything I need. I'm going to go and do my problem. So therefore that will be integral from 0 to 2 pi cosine t sine t dot product negative sine t cosine t dt. So if I'm doing this correctly, that's integral from 0 to 2 pi negative sine t cosine t plus sine t cosine t dt. Just so happen these two things actually subtracted out. So basically integrating 0 to 2 pi of 0 dt, and that would give you a 0 as an answer. All right. Hopefully good so far. So now comes the big question. What is a line integral, technically speaking? So, as with a lot of things in calculus, a lot of the driving force in the development of calculus is actually come from physics. Because a lot of time physicists try to understand how something works, but they don't know how to mathematically create the model for it. And so mathematicians come up with this model for the physicists to use. So that's what a line integral actually come down to. Is actually come from something that you learn in physics called work. So in physics, work is basically the product of force and distance travel. Okay, technically speaking, I guess I can say is basically the magnitude of force multiplied by distance travel. So therefore, you can say that work is equal to force times distance. Okay, so to calculate work is pretty easy, especially with your physics teacher. They probably consider this following scenario the most often because you just make the calculation easily. Is that, let's say force is a constant, and we're going to call that F. Actually, you know what? I can just write force for now. I don't want to give it F because I don't want you to get confused. And let's say the force is also in the direction of movement. So imagine the following. You have an object. And here's the force. Oops. And that force doesn't change. And then this object moves this way. And end up at this point. With the same exact force pointing in the same direction and with the same magnitude. So in this case, the distance traveled is right here. And since the movement are in the direction of the force, therefore I can simply say that work is just equal to this force, technically speaking the magnitude, multiplied by the distance. Good? Oh, I use a lowercase d. I guess I use a lowercase d. So that's the best case scenario. But of course, that would probably be what your physics teacher would assume is the case. For us, we want something better. Something more challenging. So how about we do a case 2? What if this is the case? Let's say that in this case 4 is still a constant. It doesn't change. But in this case, the force is not in the direction of movement. But the movement is still constant. So the direction of movement is actually not changed, it's fixed also. So, which is also under case 1, I just didn't forget to write it. So in this scenario right here, let's say I have an object. But it has a force that goes like this. Oops. And the object moves this way. And then sometime later, the object is over here. And the force still pointing in this direction with the same exact force. And here's the distance traveled. So how would you deal with this scenario? Well, let's assume that we can define the direction to be in the direction vector u. See, before there's no need to deal with the direction because the direction of movement and the force are going the same direction. And they're both fixed. So we don't have to deal with that. But now that we have a movement that's different than the force direction, now we're going to have to kind of have some way to figure out what's the difference between it. So let's say the movement is in the direction vector u. And I do want vector u to be a unit vector. And let's say we define this force to be vector F. Is that coincident that our vector field is also called capital vector F? No. That's what we want it to represent. How do I figure out how much work is being done? Well, here the problem is that the force is going off in a different direction than the movement. So therefore, not the entire force are going in the direction of movement, therefore not the entire force actually doing work. So what I need to do is actually try to figure out the component of the force that are actually in the direction of movement. And the way to do that is to actually form what we call the projection. Oops. Because when you form the projection of F onto the direction u, it will now create a force that is in the direction of the movement. And obviously that would not be the entire F, because only part of it formed the component, but it will work. And now comes the big question. Do you remember how to form the projection? Or in this case, all we need are the magnitude of the projection. And that, if you look back in your notes, we learned it in chapter 1. If I'm trying to remember, I would say 1.4 when we learned about dot products, because it's defined through dot products, is actually F dot vector u multiplied by the distance traveled. So that's pretty good. So that gives us the flexibility that if the force doesn't point in the direction of movement, I can still figure out what's going on. But of course, that still gives us a very restricted scenario, because in this scenario, the object has to move in one direction and one direction only, and therefore imply that the object moving in a straight line. But what if the object is not moving in a straight line? So that would be our case 3. Unfortunately, I kind of ran out of time. It's already 29 minutes, so I don't want to get into that discussion because it will take a while to do this. So I'm going to stop right here, and we'll continue on case 3 in tomorrow's video, or the next video, if it doesn't come out tomorrow. Alright, talk to you guys later. Bye-bye.